Now, for the final portion of the evening, I would like to invite on stage Callum Hackett. He is the head of research at Unlikely AI and Unlikely AI Lab. So, big round of applause for Callum Hackett, who's going to be talking about Introduction to Neurosymbolic AI.
Okay, good evening everyone. I'd like to talk to you about some of the technical foundations of the issues that we've been hearing about this evening. And I think probably the key reason why I'd like to give you an introduction to some of the technical specifics is because the tech landscape today can make it feel like problems with accuracy and trust are inherent to all AI systems. And that's simply not the case. I think the reality is that what we're seeing right now are the consequences of going all in on one particular AI strategy. But there are others that potentially give us avenues to alleviate the issues we've been talking about. So my plan in the next 20 minutes or so is to give you an understanding of exactly what the dominant approach is to AI right now, particularly so that you can contrast it with other possibilities. So making an argument that there is a necessity in the fact that it's going to hit a trust ceiling because of the way it's designed. And on the basis of that discussion of the design, to perhaps show a path towards how people might break through the trust ceiling. Now, if we just start with a slight historical discussion of how AI research has developed over the past 70 years since the 1950s, you'll find that research has sort of flip-flopped through the decades between two major approaches, which are referred to as Symbolic AI and Neural AI. These two approaches have been developed in many different ways by different people trying to solve different problems. But if we just keep it at a high level, in general you'll find that Symbolic AI is described as an approach which formulates explicit rules, which particularly excels at problems like theorem proving in maths and logic, but it's also at the core of most traditional computer software. Because any software application can be regarded as a kind of machine intelligence, even if it's not a general intelligence. And you'll find that most programming languages are inherently symbolic by design. And on the other side of the ledger, we have Neural AI, which is typically described as learning implicit rules from data autonomously, and that this particularly excels at pattern recognition, which is good for tasks like image classification and text generation, which is why it's at the heart of generative tools today, like large language models. Now, I'm going to develop this contrast over the course of the talk, but I particularly want to plant the thought that essentially the key battleground in AI research today is the question, where does language understanding fit in this split between symbolic and neural approaches? And so we've all got experience now interacting with large language models, asking them all sorts of questions, some simple, some complex, and finding that they can deal with them at different levels of ability. But I want to just focus on a concrete example. So here is a piece of, it's just an extract from some UK legislation, which I found randomly. This happens to be about the establishment of Great British Energy recently, but the content isn't especially important. I just want to ask the question, if you wanted to design an AI system which could rigorously and autonomously understand the content of this legislation so that it could apply it, or you could talk to the model about it, should you think of that as more like maths and logic, or should you think of it as more like a pattern recognition? And what I want to claim is that the fact that current AI systems are hitting the trust ceiling is telling us that they're answering these questions in the wrong way. So I'm going to circle back around to this example at the end of the talk to give you what I think is a sensible answer, but I want to help build us towards that conclusion by honing our intuitions about the problems we need to think through. And to do that, I just want to get you to think about two fundamentally different kinds of data that we encounter in the world and the best methods we have of modeling and understanding that data. So here's a really simple example. Just imagine you're in some circumstance where you've got some data points that you can plot in this way. It doesn't matter what the data is of. This could be mathematical data, it could be medical data, it could describe a computer program and how it takes certain inputs and produces outputs. All that matters for what we're thinking about is the shape of it. Now, suppose I said to you, we had a new data point coming, which is not on this chart yet. and I were to give you only one piece of information about it, I could maybe give you its value on the horizontal axis, or I could give you its value on the y-axis. And then I asked you to place it on the chart. Now, even though you would have incomplete information, you could make that placement perfectly. You would just follow along the one axis that you know the value of, and by eye, you would find where it sits on the curve. And the reason you can do that is because you can see that this is a regular pattern, and what that means is you intuitively understand that you can formulate a rule which allows you to draw a smooth line that connects all of the points. And what you do with that line, essentially, is predict for any new data point that belongs to this distribution with perfect precision where it should go. But now let's consider a second kind of data that we commonly find. If we were to do the same task, I said you had a new data point, I gave you some incomplete information about it, and I asked you to place it on the chart. You could make a pretty good go at it with this distribution, but this time there's a high chance that you won't get it perfect. And the reason for that, as you can tell, is that this is a noisy pattern. And what that means fundamentally is that you can't formulate a rule which will allow you to draw a smooth line through all of the points. You can still formulate a rule which will give you a kind of best fit line, which is as close as possible to all of the points. And you can still use that rule to make predictions, but now you can be certain that those predictions will have a margin of error. And that margin of error is just the difference between where the line sits and where the data points are. It's the difference between expectation and reality. So we've got these two different types of data that I want us to think about. And when we're keeping data simple with the kinds of shapes that I've shown here, in both cases, you can formulate rules. And whenever you have rules that you can use to make predictions, you have things that you can write down, you can understand, they're transparent, you can manipulate them, you can control them. But when we start trying to automate our modeling of this kind of data, and when we start adding complexity to the picture, this is when we start thinking about AI, and it's when symbolic and neural models really come into their own. So let me then talk about adding some complexity to our picture. If we think first about complexity of regular patterns, there are many types of complexity we can consider, but I'm just going to pick out one which I think is salient. We find that there are certain kinds of regularities that build up essentially patterns within patterns. And so if you look at this data shape, you can see it has broadly the same kind of S shape as the previous data shapes I showed you. But you can also see now in the tails at the top and the bottom that there's this repeating wave shape. And when I say that you can have patterns within patterns, I just mean you can do this thing of taking apart the data, looking at it at different levels with different lenses and finding that there's regularity at different sizes. But you can still tell intuitively, when you look at this, that there is a smooth line that you can draw through all the points. And what that means implicitly is that just as the patterns build on top of themselves, you can formulate rules that stack to continue making perfect predictions. And this is where symbolic AI traditionally excels. You don't have to use symbolic AI for this kind of data, and I'll talk in a moment about how people are trying to use alternatives. But symbolic AI, in its essence, is just about formulating rules which deal with simple regularities that compose together to build complex regularities. There is a different kind of complexity, however, which symbolic AI finds it harder to deal with. And this is particularly relevant when we're talking about noisy patterns. And here I want to think about adding new dimensions to data models. So you might remember from a few slides ago, I showed you that noisy S pattern where I had two axes. There was the x-axis and the y-axis. And here all I'm doing is adding a third one, the z-axis, to make it three-dimensional. Now, we do this often to try to make it easier to find patterns in data. And an intuitive reason to understand why that's the case is because if we've got three dimensions here, it's as if you can peer around the sides of the data to spot relationships between those data points that you wouldn't see if it was collapsed in only 2 dimensions. And this time, instead of drawing a line that represents our ability to make predictions through all the points, you have a 2-dimensional surface, but it has exactly the same function, where we say anything that sits on that surface is a prediction that we would make, and that surface is there to try to sit as close as possible to all of the data points. Now, the reason why this, as I say in the slide, is where neural AI excels today is because once you start adding these dimensions and once you start getting these complex, quite uneven surfaces, it becomes more difficult to formulate explicit rules to describe those surfaces. In a sense, neural models are learning those rules, but they're not formulating them explicitly. It's the implicit learning process that makes this possible. And what that looks like in very simple terms is you'll start with a model that makes an initial guess at what the predicted surface should look like. It might just be random to begin with. Then it will make a prediction, and you'll give it some feedback about the quality of that prediction. And using that feedback, it will make a change in the predictive surface to try to optimize it and make the predictions better. And you go through many of these feedback loops until the improvements can't be made any longer. Now, it's important to understand the immense complexity that modern neural models are representing in undertaking this process. You could imagine, as a baseline, that you might want to try to represent the meanings of words in a language like English, and you could do that by going through a dictionary and giving every word coordinates on X, Y, Z axes, and you could plot all of the words in a chart like this, and the distance between them would represent their similarity of meaning. In a very simplified way, that is what language models do, except instead of using 3 dimensions, they use literally thousands. And not only can we not visually represent those dimensions because we can only see in 3, and there's no high fidelity way of representing that in a 2-dimensional chart, it takes us beyond the point where we can even begin in practice to formulate those rules, which means we end up with what we understand as black boxes, where we can see certain relationships between inputs and outputs, but we can't inspect the predictive process itself, which is generating the outputs from the inputs. And I want to stress with this that in many cases, you have statistical predictive systems where margins of error are natural and perhaps not even that damaging if you can see how those statistical systems are working. But when you have black box models in particular, their black box nature multiplies the impact of those margins of error, because you can't systematically inspect how the predictions diverge from reality, and that means you can't build up a solid understanding of when and why those errors are occurring, so you become much less effective at mitigating those errors. And in the end, the reason why the hallucination problem is particularly damaging for trust is because not only do you have to accept the fact that mistakes will happen, you may not even know when you're looking at a mistake. Now, many people in the AI industry have been hoping that by making iterative improvements to neural models, that the hallucination problem and other kinds of errors will become negligible. And there's also been an implicit hope and expectation that improvements to models will allow this learning process to learn complex regular patterns just as well as they learn complex noisy patterns. But I think we have some principled reasons to believe that on certain kinds of tasks with regular complexity, these models will always plateau at performance rates that are less than 100%. And I want to give you just a visual thinking tool to explain why that's the case. So with this image, you can see a fractal. And a fractal is just a mathematical object which contains a special kind of regular pattern where the regular patterns build on top of each other up to infinite detail. And so what that means is I could take any part of this image and I could zoom in and I would see in full resolution more detail. And I could keep zooming in indefinitely. There would always be more detail for me to find. And I'm still thinking here in quite general terms about data shapes that apply in lots of domains. I'm not thinking of this specifically as a mathematical object. You do get fractals in maths, you get them in computer algorithms, you can think of the evolution of species and the evolution of language as having branching effects which are like fractals. So I'm just thinking of this as an abstract data shape. Now when you have these kinds of regular patterns which build potentially up to infinity, because they're regular, you can model them very effectively with symbolic models. And indeed, symbolic algorithms were used to generate this image. And so if I were to take any part of that image and I were to zoom in using a symbolic algorithm which describes it, I would find the full detail that I want to find there. But if I were to think what would happen if I took the data set that's represented by that first fractal image and I tried to train a neural model on it, and then I chose a portion to zoom in on, I would get something which effectively looks like this, where the detail is all a blur. What this is representing is that neural learning methods are only good at making predictions which match the granularity of the data that you feed them when you train them. And so we didn't give it data for this particular zoomed-in portion when it was trained, and that's why when we zoom in, we find it's blurring. Now, with any specific instance like this, you can always throw up your hands and say, okay, give it more data. And in this case, you could absolutely do that. But the problem in principle is that when you have this kind of fractal regularity, you are producing potentially infinite novelty. And neural models cannot train on infinite data using infinite energy. That's why we will always find, in some use cases, a plateau beneath 100% accuracy. So this leads us to the guiding principle of Neurosymbolic AI, which begins by recognizing that there is this distinction between regular and noisy data, and with the recognition that different approaches to AI are suited to different tasks. And so Neurosymbolic AI says the most sensible thing is to have a division of labor between these different approaches. So you have your data, you split it into the regular and the noisy parts, and you use the tool which is fit for the task. As you might imagine, this is somewhat easier said than done. There is some art in the science of it. And that's especially because in many domains, you find that the data contains regularity and noise at the same time, intermingled with each other in a way which isn't entirely easy to separate. And so I can look back to this example of the UK legislation to give you a glimpse of how that works. In this case, you can find in this text that there are regular patterns which are sort of fixed structural features, which here certainly don't develop to infinity like we saw in the fractal, but they're properties that have the potential to develop in an unbounded and predictable way. So you have sections, clauses, and subclauses, which iterate in fixed, predictable, numerical, and alphabetical sequences. You have indentation relationships, which are encoding rigid hierarchical relationships. And you have links between sections, which are encoding fixed logical relationships. These are all regular patterns, which are very easily amenable to symbolic representations. And when you use a symbolic representation, you get all of the advantages of transparency that comes with that. So you simply don't have to settle for the approximations and hallucinations of neural models when you have these kinds of patterns. And again, as I sort of suggested with the fractals, for any small portion of data like this, you can look at it and say, this isn't a problem in principle for a sophisticated neural system. But as you start adding to the size of data under consideration, say if you were trying to get an understanding of the entire body of UK legislation, you will end up with intractable problems with neural models and their lack of precision. At the same time, however, whenever we're looking at language data, we are also always looking at noisy patterns. So here, for example, under 3A, just to pick an instance, we've got some wording where it says, must specify the time from which the designation has effect. If it so happened that this legislation was written to say, is effective instead of has effect, it would make no substantive difference to the meaning of the legislation. And that kind of interchangeability is effectively a sort of semantic noise, which neural models are much more efficient at screening out than symbolic ones. And similarly, in 3B, we see some language we might consider to be somewhat vague, where it says that something must be done as soon as reasonably practicable. And if you wanted to achieve an automated understanding of that, you might find that there's a lot of contextual nuance involved in interpreting it, where the high-dimensional representations of a neural model are likely to be more capable than a symbolic model. So a key insight from this is that there's no need to say that we should perfect one kind of AI, like neural models, to try to solve every problem with the tasks that we're trying to address in some use case. And likewise, we're not saying that we should take data and try to represent it from top to bottom completely symbolically. What we're saying is, if you can identify that there is regularity in your data, you can use symbolic models to represent it. And we know that wherever you can use symbolic structure, you can build trust, because inherently symbolic models are explainable, because it's in the nature of symbolic representations that you can inspect them, you can validate them, you can control them. It's also inherent in symbolic models that they're consistent, because it's in the nature of symbolic rule following that it always happens the same way every time you run it. And it will be accurate just so long as you have correctly identified that the data is regular and you've got a model that fits in the same way that we saw at the beginning with that S shape, that you could always predict perfectly how the data would fit on the curve. Your predictions in this case will always be accurate as well. So I just want to leave you with two final thoughts. The first is that I think actually it's an open secret in the AI industry today that neurosymbolic methods are the path forwards. And what I mean by that is, if you look at the way platforms are being developed by the big model providers, they're augmenting generative tools like LLMs with things like web search, with code generation, and various abilities to make API calls to other software tools and so on. And that's because there's an unspoken consensus that generative tools like large language models are not going to be the all-purpose systems that people were hoping they would be. And whenever they make a call out to some other tool, that call is itself a kind of structure which is introducing the possibility of symbolic representation, and often the tools that are called to themselves have symbolic content, which is especially the case with code generation. And I think, though, it's important to not embrace the neurosymbolic outlook in a sort of hushed and haphazard way. We want to embrace it proactively so that we can come up with coherent research programs which understand that the key problem here is to develop systems which are able to autonomously separate the regular from the noisy. And I think this is vital, moreover, because this is the only outlook, in my opinion, which I think is capable of sustaining further progress towards general intelligence. And the reason why I say that is because on the previous slide, when I was showing you the example of the legislation, what we were looking at was an example where it's very clearly visible where the differences are between the regular and the noisy patterns. But one of the key tricks in human intelligence, which makes us special, is that we are able to take noisy information and with care and time and analysis, we can find useful regularities in it. And that is essentially what the scientific process is. We inhabit the world and we get an onslaught of noisy information through our senses, but we develop science and technology by formulating that information in scientific theories, which are essentially rule-based systems. And so this noisy perception and rule-based understanding in humans is the paradigm example of neurosymbolic intelligence. And I think the exciting prospect of automating scientific discovery is the logical endpoint of developing trustworthy neurosymbolic models today. Thank you.
Light working? No? Yep.
Great. Thank you, Callum. That was awesome. So yeah, we're wrapping up. So I just want to say some thank yous. So thank you in particular to our panelists, Monica, Matt, and Tim, and to everybody, all of you for coming. Really appreciate it. This isn't over. I'm just about to say what the next stage is. We've got bowl food coming up, but this is sort of end of the formal part of the evening. And of course, thank you to Paro and the team for all of the organisation. Lots of people in Unlikely AI were involved in organising this event. So thank you, you guys. And I also just want to quickly remind you about the embargo. So any photos you took, please share them on social media. It's fine, but not the ones with data in. Not until Tuesday morning at 8:30 a.m. when the embargo lifts. So please tweet and post on LinkedIn about the data, and you can post pictures of the event and talk about it without the data before then. We now have food and drink. There's bowl food. Anybody that wants to stay, so we can circulate and talk more about the importance of trust. Thank you.